Hello and welcome, dudes and dudettes. Remember that game I'm making that's not really a game yet as it has no gameplay, but I'm doing stuff with it? So I did some stuff with it. After the last devlog we got a planet shape and some material, so the next logical step would be to start working on game mechanics, of course. Or procrastinate and work on some more interesting stuff like clouds and atmospheric scattering. Maybe we can even tackle saving system in this video. Let's start with atmospheric scattering. To not waste time, I immediately started searching for already implemented solutions. However, it turns out it's hard to find already implemented solutions that would work with a spherical planet. Actually, the spherical nature of my world often causes everything to become more complicated than I wish, but life is life. So after finding quite a few amazing solutions that do not work with my planet, I finally borrowed the implementation from some less known YouTuber Sebastian Lake. Well, as I'm already here, let's just yoink. Wow, this is gonna be an easy video. Oh, well, okay, we're gonna have to do some work after all. I'm pretty sure I already explained how I made Sebastian's implementation of atmospheric scattering work with Universal Render Pipeline in some previous devlog, but I'm pretending those previous devlogs do not exist, and a lot of time passed since then and a lot of things were changed to the point where I could no longer tell you what I did step by step to get from this, through this monstrosity from my previous devlog series attempt, all the way to the current one. So let's just discuss the key parts that I remember and some new stuff I did. So how to get from this to this? Well, it's actually not that hard. Step 1. Create atmosphere settings file. Step 2. Create atmosphere bleed path. Step 3. Create atmosphere bleed future. The point of bleed future is to run bleed path, and the point of bleed path is to run shader on the entire view without bounding it to some object. It basically creates a quad over the entire screen and allows you to run shader on that quad, as general shaders have to run on some kind of object. Anyways, step 4. Create cloud settings file. Step 5. Update atmosphere bleed path and bleed future to include clouds as well. Wait, what the fuck? What? How did we ended up adding clouds to atmosphere? Well, that is actually a very good question. Let's do a quiz. Option A. Merge them to have less lines of code. Option B. Merge them for performance reasons. Option C. Merge them so atmospheric scattering color could affect clouds color. Option D. Merge them to reuse methods. Option E. Merge them because I couldn't make clouds bleed path work on its own. And if you chose option E, you're incorrect, but solid choice. Definitely something I would do. The correct answer was C though. If you chose A, well, fuck you, I'm not that stupid. Well, I mean, you kinda just created a quiz in a video that no one will watch live and made up the results, so... No one likes you. You realize that I'm you, but with edited voice, right? Anyways, the fusing process was quite simple. Once we have bleed future and bleed path, we can set all the settings from both clouds and atmosphere setting files and simply copy all clouds related methods to atmosphere shader. The shader itself has a lot of code that was stolen, borrowed, fused together and updated a bit. And the result of this is the master atmosphere with clouds shader that provides, you guessed it, atmosphere and clouds in a single bleed path. This amazing monstrous shader is written in HLSL. You may be wondering, what is HLSL? HLSL is short for High Level Shader Language, and this is the lowest level language I worked with since university, where we wrote some small algorithms with assembly. It's like C with less futures. Anyways, enough ranting, let's go through a quick overview of how this thing works. So the shader has two main functions, vert and frag. Vert runs on each vertex of an object the shader is applied to. In our case, this means it runs on 4 vertices of the full screen quad. When the values of things like vertex coordinates are interpolated and passed to the frag function. Frag runs on each pixel the object occupies, in our case the entire screen. Each call to the frag function will receive the interpolated data from the vertex function. This, for example, allows us to know the coordinate of the pixel we are working with. And that is quite useful, as using that we can sample things like depth texture, whatever. As mentioned previously, the core code of actual atmospheric scattering and cloud generation is copied from Sebastian Lake's repositories. And as we already explained how the shaders work in our videos, I probably won't add any value explaining again. Nor do you understand them enough to do that, There are only a couple of important modifications to mention. Firstly, Atmosphere Shader now only works to a certain depth. After that, exponential squared fog is used to add some darkness to the deeper layers of the planet. This is not actually a correct approach to this, more of a temporary hack to not have planet center shining like a sun. The actual fix should probably include decreasing the light intensity the more distance it travels through the atmosphere. As it stands, it seems to add the light for each point being checked. That results in lighting becoming much more intense when traveling towards the center of the planet. For now, I'm using my hacker solution as I'm still too dumb for something more advanced though, so... Another important modification is merging color of atmosphere with clouds. Basically, once we calculate clouds value for the same pixel, we merge it with the original color with atmosphere already applied using the following function. Clouds are also made darker based on the angle between their position and sun, counting from the planet center. If the clouds are the same direction as the sun, we have lighter color, and if they are in the opposite direction of the sun, we have darker color, as if the planet would cast a shadow on them. Okay, the final solution is not ideal again, but I spent a lot of time messing with it, and that's the best I can do without investing at least a bit of time into learning how the colors combining works in shaders. And I should probably do that someday, but that would include reading, and reading is for nerds, and I'm not a nerd, just wait a minute, what am I, geek maybe? No, what is the difference? Nerd versus the geek. Okay, dork, silly, out of touch, yeah, that's quite close. Socially awkward, intelligent, nah, not me. Expert, maybe? Phoebe. Unintelligence, fusion of dwarf and Phoebe. Well, I don't know what any of these words mean, so probably I'm a dweeb. Additionally, the current implementation has this issue where if you are close to the starting line of clouds, it looks kinda weird. This is because the cloud's noise is not cut off naturally but rather using smooth spherical surface. I intend to fix all of these issues in the future, or I'm just gonna call this game early access in Steam and have it as is for the next 5 to 10 years. That's the normal amount of time modern games should be in early access, right? Right? Anyways, enough about clouds, let's go to something simpler, like the saving system. If you watched the previous devlog, you know that under the hood our planet is made using 3D volume of points. This volume is used to generate the mesh using Martian cubes algorithm. As the planet is massive and can be edited by the player... Wait, did I mention that in my previous devlog? Whatever. We need a way to save what was edited. The planet noise is generated procedurally, and saving it to a file would cause us to use a lot of storage per planet, so the solution is to only save the edited points. That includes saving edited point coordinate and the value. Of course, that isn't so simple, as we are using Octree to have different resolution chunks. Because of that, I had to choose to either load edited points of smallest possible chunks when generating large low resolution chunks, and that of course is a bit slower and uses a lot of memory, or save the same edited point for multiple different resolution chunks that include that point, and that basically means duplicating data. I chose the latter because that helps to save memory at runtime, as we don't need to load all data in highest resolution. And trading storage to memory is kinda reasonable trade-off. Also, the storage usage does not increase that much, as each lower resolution chunk has only 1/8 of the points. So if we want to save 8000 points in highest resolution chunk, we will be saving 8000 points in highest resolution chunk file, 1000 points in its parents file, 125 points in its grandparents file, about 15 points in its great-grandparents file, only 2 points in its great-great-grandparents file, god this is confusing, and overall this approach increases storage usage only by around 14%, and that's quite reasonable trade-off. It also makes points editing method a bit more complex, as now every time a point is edited we must check if that point is also in the parent chunk, and update that as well. However, performance impact of this is negligible and the computation is not that complex, as my chunks already know who their parents are, unlike you. The saving itself is a bit more complicated than it could be. The first implementation was of course simple. I took each axis coordinate and the value and saved it to a file. This meant that the total number of bytes needed per edited point was quite high though. 4 bytes per coordinate axis plus the value of the edited point, which at the beginning was floating point number, so another 4 bytes, giving us 12 bytes in total. 16 bytes in total, I suck at math. However, as our chunks are quite small, 18 points per axis each, it is enough to use 5 bits per axis to save the coordinate. Also, float resolution of value of the point is also higher when necessary, so I change it to only use 1 byte. In this byte, 7 bits indicate the actual value and one most significant bit indicates if the point was edited or not. Because of this, we always know if it should be saved or not. After all this, the amount of memory needed per edited point decreased from 16 bytes to 3 bytes. So after some small bit shifting, our saving system is now much more efficient. After all that, if we want to load the planet, we can load noise the same way as previously, generating it procedurally, and then load edited points from files and override noise values with them. This works quite nice and the storage usage is quite low. I could have used simpler, more storage intensive method, however, over-engineering is quite fun sometimes, so here we are. Anyways, that's kind of it for this devlog. Just wanted to get these half-baked things out of the way before working with something more important, like placing of resources in trees, which turned out to be way more complicated than I expected, to be honest. So if you won't see another devlog for a year or two, it's probably because I failed. Or I was attacked by the King Voldemort from the Lord of the Rings Return of the Jedi movie, who knows.